Alright, gentlemen, I'm going to try and fly through this. I wish we could have gotten it done in class. Okay, we already talked about rotational versus revolution. So 10.1 was rotation versus revolution. Okay. So what you should know about that, a rotation is around a center axis. So that's like the Earth rotating in a circle. So that would be our Earth. He has an axis and it rotates around it. Okay, he just keeps spinning on that internal axis. It's inside of him. Okay, the next one is revolution. This is around an external axis. Okay, ultimately that is the Earth revolving around the Sun. So here's the Sun, and all the planets revolve around it in an orbit. This would be an orbit. This would be a spin. Alright, that's how you can think of them differently. Orbit versus spin. Okay, moving on. We apparently had trouble with 10.2, so I'm going to call it speed. Now, since having the different names threw some of you off. Okay, linear. A linear speed is any speed in one direction. Okay? No moving. So on a circle, this is that foxtail explanation. If you're spinning something around and around, eventually if you let go, it's going to go off in one single direct speed. Linear speed is speed in one direction. It's also, go back. This is distance over time. That's your standard distance over time equation. Alright, next up, after we do linear speed, we have tangential. Okay, this is the same thing as linear. The only difference is speed in a direction. Moving in the path of a circle. So the second drawing I have, that is technically a tangent, because at one point it was going around the circle. So I drew this in class. Don't have my perfect here. We put our nice perfect circle in. At any point on this line, if I draw an arrow, we're going to have an arrow here. We're going to have an arrow here. There are ultimately infinite numbers of tangents. So we just find like the average of that tangent. They're usually given. Okay, next we got into rotational. All rotational is it's dependent on your location in the circle. It is number of rotations in a given time frame. Okay, so if you don't make a whole rotation, you make part of a rotation. That's maybe like a 45-degree rotation. But no matter where you are on this plate or on this circle, your rotational distance is the same, or your rotational speed is the same. Because I'm making a fourth of a rotation, I'm making a half of a rotation, I'm making 3 rotations, all the same. Okay. Now, what I was getting into with the equation for rotational and tangential speed. Okay. If it really throws you off, just say equals. V equals radius times omega. So I wonder if I can find that real quick. I'm not going to spend a lot of time. Symbol. The omega is a weird looking W symbol. Of course, I'm not going to find it. Kind of like that, but I'm going to search for days. curious what we're going to get into them. Apparently not. Okay. Okay, so I'll just draw it and cancel. Okay, omega, yes, it's this symbol. I'm not arguing why or how come, but it's this weird looking extra loopy W. If you want to question it, read the book, whatever. This is what they chose to represent rotational speed. So what each of these are, this is velocity equals radius times rotational, which is r times rotational speed. Okay, why they chose omega beats me, but that's what they did. Alright, and then go into the history there. What I was trying to get at with that spinning, so every speed is going to be different. So when I was getting into the train situation, if you take a cup that has a wide neck, when it spins, it's going to spin in a circle. The reason why is the radius here is much greater than the radius here, which causes it to spin in that circular motion versus just spin straight down the line. If you had a perfectly cylindric cup, it would spin directly and straight, but instead, as you change the radius here, bigger radius, smaller radius, it rotates. It has a rotational speed. So when you think about the train, you got your train wheels here, your train wheels here. The reason why they're built like this is that when they take a curve, they spin, because this cup, because the larger radius here allows this to adjust for the curve. So if the curve is going outwards, you're going to bank up on the track. If the curve is going inwards, you're going to bank down on the track. You're going to be down on this side. So the radius depends on its rotational speed of that. Okay, that's all I'm going to go over. Not a big thing right there. Okay, where we stopped, where we could not go on, centripetal force. That is 10.3. Centripetal force deals with this inward force. I'll write it over here. Okay, this is an inward force. Inward force on a cup or a body, usually like a tension. So if you're spinning water in a cup on a string, this is tension force. If you are on a racetrack, this is frictional force. It's always an inward force on a cup or a body in motion. Okay, so when you think of the racetrack, it occurs because of the friction, not actually because something's pushing back on it. It's a great example with a race car. As it spins around the track, it has that friction. Now, the reason why a race car is banked is it helps affect that friction. Alright, now we have an equation that goes with this. The equation, I'm just going to copy paste it for lack of time. There we go. So the equation looks like this. And there it is. Okay, centripetal force is mass times speed divided by radius of curvature. So we have our circle. Here's your radius. This is the radius of the curve. And then your speed. So that's how you can calculate it. That's all we're going to get to today. Oh, centrifugal force, 10.4. I may have spelled that wrong. Centrifugal force, this is usually a fictitious force. I spelled it wrong. Sorry about my husband there. Acting, now I've lost. Acting outwards. What that really is if you've ever taken a right in a car and flown your body, played that like Jello game with your brother or sister, where you all flop to the right, or then you take a left and you all flop to the, you take a left and you flop to the right, so on and so forth. It's that inertia force. I'm really struggling now. Okay, I have to go. You're going to have to just deal with this for now. We're not going to worry about 10.5 for now, but ultimately this is centrifugal is a fictitious fiction for sure, acting outwards. Ultimately, it's your inertia of your body wanting to stay in that direction, and the object, like seat belts, stopping you. Alright, hope this helps. Good luck.